students, in physics in the section waves and oscillations, we are going to see another experiment now. Actually, this experiment is quite a simple one. We are not going to get any readings, we are not going to do any calculations. It's just about observing the properties of waves. So, when we study the theory, we study few properties of waves, right? The transverse waves, longitudinal waves, we studied properties. There are some common properties, there are some different properties. We studied a lot of properties. To observe or to verify these properties, there are different instruments. For example, there is slinky. We can use slinky and observe certain behavior of waves. And then we have a vibrator, right? This vibrator can be connected to the a string, a stretched string, and when the vibrator vibrates, string also will get the waves. There will be a wave that will be traveling through the string, and it might go and get reflected on the other side. Then we may be able to see standing waves. Likewise, there are few practicals or few experiments we can do with certain instruments like slinky, vibrator, right? There are many others as well. There is another dot vibrator. We can use it in the water surface and generate waves, and we can observe the behavior. Likewise, there are a lot of different apparatus available in the science lab or physics lab to observe the behavior of waves. Here I am going to take slinky and a vibrator and observe or verify few behaviors of waves. Right, that's what we are going to do. Look at this again, verifying the properties of waves using slinky and stretched string. Properties of waves that you would have studied in theory. Reflection. That means from when the waves, when they go and reach one end of its medium, it can reflect, right? Refraction. When waves penetrate from one medium to another medium, there can be a refraction. For example, look at this reflection. I will show you. Let's say you have a string like this which is connected to a wall, and then you are vibrating at this point. Then a wave will travel like this. This wave, when it reaches this end, now that's the end of its medium, it can't go further. Then it will return, it will get reflected. So what will happen? You will see a returning wave also like this. Because it reached the end of the surface, end of the medium, it returns backwards. That's what we call reflection. Refraction means this is on the string I am telling. Even in other mediums you can see this, you can observe this. Refraction means, think you have a thick string which is changing into a thin string afterwards. So the wave that travels from here, when it enters into the thin part of the string, its velocity is going to change. Why? You know, V is square root of T over M. T is the tension on the string, which can be the same throughout the string. M is the mass per unit length. So mass per unit length is high here. When the string becomes thin, mass per unit length is low. Then what will happen? Compared to this part, here the velocity will be high. Why? When M decreases, V will increase. Velocity high means with the same frequency, when the wave travels, V equals F lambda. F is a constant, same frequency. When V increases, lambda also should increase. So after this, you may be able to see increased lambda. The width will increase, right? So this is a phenomenon of refraction. Refraction means from one medium to another medium, when the wave travels, when the wave penetrates, its velocity or its speed changes. Sometimes the direction also might change, right? So that's what we call refraction. Diffraction is where when the wave travels through a small opening like this, it gets diffracted rightly, like this. That's what we call diffraction. Polarization. Polarization applies only to transverse waves. Polarization means, see, let's say a wave travels in this direction, a transverse wave, right? So the vibration of the transverse wave can be in different planes. One can be like this. Likewise, it can go. This is like on the plane of this board, the vibration happens. Sometimes it can be perpendicular to this board as well. See, when one wave is vibrating like this, other one can be vibrating in another plane. How do I draw that? See, this is in a different plane. This is in a perpendicular plane like this. Right? So one is vibrating in perpendicular or vertical plane like this. Another one is vibrating in a horizontal plane. Another one can be vibrating in another angled plane. Likewise, transverse waves can be vibrating even though all of them are going in the same line. The direction is same. The vibration can happen in different planes. What we mean by polarization is we can use some techniques and after a point like a filter, we can use a filter and let only one plane waves to the other side. When vibration happens in different planes, you filter it and only the waves in one particular plane can pass the filter and go to the other side, which is what we call polarization, which we can even observe with slinky, right? When slinky, like let's say you keep the slinky like this, give a perpendicular vibration, and then you keep two blocks there, just keeping a small opening, keep two boards, right? Look at this. You keep the boards like this. This is where slinky is. This slinky, if you vibrate vertically, in this direction, if you vibrate, that vibration, that wave can penetrate through this opening, right? Because in the same plane you have the vibration. Imagine if you vibrate the slinky like this. From your hand until the point of this board, the vibration can go, the wave can go, but after that wave will not be able to go because this board is going to block it. I'll show it when we do it with the slinky. I'll show it how we can observe this. So this is what we call polarization. So these are some of the features that you would have studied in theory. Now some of them we are going to observe in slinky and the stretched string. Materials and apparatus required: slinky, vibrator, a stand to fix this, a string, pulley and set of weights. Why do we need pulley and set of weights? Look at this, the string, one side it will be connected to the vibrator, other side we will take it above a pulley and we will connect it to some weights. Why is that? As I mentioned earlier, V equals square root of T over M. I want to change this tension so that velocity changes because M I can't change, it's the same string. So I am going to change the tension and change the velocity, right? Why? V equals F lambda. So when V increases, lambda will increase, to observe that. So how do we increase the tension or change the tension here? By changing the weight here. You change the weight connected there because you know why? The weight is W, T, T must be equal to W. And if it is a smooth pulley here, that same T should be here. Same T should be here. Understand? So tension can be changed by changing the weights that we fix here. For that we need a set of weights as well. Look at the procedure. While holding one end of the slinky rigid, if the other end of the slinky is moved perpendicular to the slinky, rigid reflection of transverse waves can be observed. Rigid reflection means, look at this, the wave will travel like this, and at this point if the reflection happens, the returning wave will be having a phase difference like this, 180 degrees phase difference, right? It will be in the opposite phase, yeah? That's what we call rigid reflection, When this continues, standing waves can be observed because one wave is going to be going in this direction. Same wave is going to return in the other direction with 180 degree phase difference. So there will be a standing wave. You can observe standing wave. While holding one end of the sling is soft. Soft means Like here, rigid means you have fixed it to a wall, something like that. So this end cannot move. This end is rigid. Or the person holding it is holding it very tight. But if that end, the end where reflection happens, if that end is free to move, you are holding it freely, softly. So whatever the way it wants to move, you give freedom for it to move. Or let's say you have hung that point using a thread or using a, say, rubber band. Then, that end is free to move, right? Then we call it, the reflection that is going to happen will be soft reflection. See, soft reflection. If soft reflection happens, if this is the progressive wave, the returning wave also will be in the same phase. When it reflects from here, that also will be in the same phase. Not a phase difference there, right? Once the transverse waves are produced in a slinky, if two boats are kept parallel and close to the slinky, the fundamentals of polarization can be understood. I explained earlier, like polarization means the planes of vibration are different. Polarization means we allow only one plane of vibration to go passing the filter, all others to get blocked, right? So that we can we can understand here also. Connect one end of the string to a vibrator and the other end with known weights and start the vibrator to observe standing waves on the strings. Yes. By changing the weights, different overtones can be observed. What is the meaning of overtones here? Look at this. Say this is a string. Right. Let's say this is the wave that travels here. After this, you have the pulley and the weights. Then it returns. It's a rigid reflection. So you will see phase difference like this. Yes. So now you see 4 notes here like 1, 2, 3, 4. V equals F lambda. In the meantime, V equals square root of T over M. Now what we do? Increase T. Then V will increase. When V increases, lambda has to increase. Lambda means this gap. So now you see 4 notes here. When T is increased, at some point you won't see 4 notes, you will see 3 notes. You will see something like this. See, like this. Only 3 notes. Understand? Why? When tension increases, velocity increases. And because the velocity increases, the vibrator's frequency you did not change. So, same frequency, V increases means lambda has to increase. So, now you see only 3 notes. You keep increasing the tension, you will see 2 notes. Right? So, this way we can understand when tension on the string changes, how the speed of the wave changes and how the number of notes that we observe changes, all that we can see here. Right? So, this is what we are going to do in this experiment, understanding and verifying certain properties of waves that we studied in the theory. So, there won't be any readings that we are going to take from here. There won't be any readings, there won't be any calculations, just mainly observing the properties of waves is the main thing that we are going to do here. Right. After that, we will do some past papers, not directly from this area, from this experiment, maybe connected to this, but from other areas also, like whichever connected to the properties of waves, we will take the past papers and do after doing the experiment. Right. So now let's take a slinky and see how we can observe the properties of waves. Alright students, now let's see some past paper structured essay type questions which are related to this experiment that we have done. Right. Let's start from the very old one, 1988 paper. In an experiment to analyze the properties of standing waves, one end of a rubber string is connected to a vibrator and its other end is connected to a rigid stand. The distance L between the vibrator and stand can be changed. The diagram drawn to scale shows the string vibrating in its frequency. Right. So, you can see, we see a standing wave here. Lambda by 2 is 20 centimeters. So we can find lambda is going to be 40 centimeter. They have marked the amplitude also. Careful, like if they ask me to find the amplitude, I will find based on the graph I have here. But in the exam, the original diagram would have been different, right? So if you see the original past paper, sometimes the size could be slightly different. Using this diagram, find the wavelength and amplitude of the vibration. See, that's the very first one they ask. Wavelength has to be 40 centimeter, right? Wavelength means this much. 40 centimeter. Amplitude, this is like, how do we measure it? In the exam, what you can do, you have a ruler. So keep the ruler and find from here to here how much centimeters, here how many centimeters, you can find like that. Here, let me do something like this. Let me draw a line like this. Let me copy and paste that line to see how many times I am getting it. Second one. Third one. Almost 4 times we are getting. So you know, this is altogether 10 centimeter, this much, because altogether both boxes together it's 20 centimeter. So one division must be 10 centimeter. Of that 10 centimeter, this is 1/4. So 2.5 centimeter is what I see in the graph, in the diagram I have, right? But in the exam, what you do, you take the paper, keep your ruler and see how much you get. So I can say it's 2.5 centimeter. Wavelength is 20 centimeter. 20 or 40? 40. 40 centimeter. And this is 2.5 centimeter according to the diagram I have. What are the types of motion that the particles at node A and antinode B will undergo? Node A, antinode B. Node A means they have not marked it here. This is node A. Node. This is where antinode is going to be. Antinode B. So node A, the particles will be at rest. They don't vibrate. Antinode, the particles will be vibrating with the highest amplitude. Because anything in between, they also will be vibrating, but the amplitude is not the highest. Right? So we can say A particles will be at rest. B particles will vibrate with highest amplitude. Highest amplitude. Next one. The wave speed V of this wave can be expressed as V equals square root of TL over M. Here T is the tension in the string, L is the length of string and M is the total mass of the string. See, usually we study V equals square root of T over M, where this M is mass of unit length. That means this M is going to be total mass divided by total length. So when you substitute here, you will end up having this. Square root of L will go up, TL over M. That's what they have given. Show that the dimensions of the right hand side of this equation are the dimensions of speed. We have T. T is tension. The dimensions must be that of a force. Force dimension MLT minus 2. L is length. L. M is mass. So when you say square root of TL over M, MLT minus 2, L over M, since there is a square root, let's put half. M and M will be cancelled, L squared T minus 1. LT minus 1 will come out. L squared T minus 2, when you take power half, square root, L and T minus 1 will come. What is this? This is the dimensions of speed. Speed is distance over time. L T minus 1. L T minus 1. The natural length of a rubber string is 1 meter. When the string is extended to a length of 1.4 meter under Hooke's law and vibrated in its fundamental frequency, the wave speed is 18 meter per second. If the tension and extension of the string are T and E respectively, what is the relationship between T and E? You know, T is proportionate to E. T equals KE. T equals KE or lambda E. K is a constant. K is a constant. That's what the Hooke's law is, right? T is proportionate to E. If the string is extended to 1.2 meter and the new tension is T dash, express T dash in terms of T. So T is, look at this, K into, the natural length is 1 meter. When it was extended to 1.4 only, it was T. So the extension is 0.4 meters, right? 1 to 1.4, 0.4. K into 0.4. T dash, K wouldn't change for a given string. K wouldn't change. Now you are extending it to 1.2 meter, means extension is only 0.2 meters. Extension is 0.2 meters. 2 over 1 T dash over T is, when you divide it, K cancel, 0.2 over 0.4. So T dash will be half, 0.2, 0.4, half T. Half T. At the new length of 1.2 meter, if the string is vibrated in its fundamental frequency, what's the wave speed? See, at 1.4 meter, they have given the speed as 18. So, you know, V equals square root of T L over M is the formula they have given. Right? First case we will write V is given. V is given. How much was it? 18 meter per second. So 18 T L is 1.4 meter it was M. Then we have V dash now, T into T dash. T dash means T dash is half T. Let me say T dash for now. Length is 1.2 meter, right? Then you can say V dash by 18. When you divide these two, M and M will be cancelled. V dash on the top, right? T dash into 1.2, T into 1.4. V dash will be 18 into T dash over T is half, right? See, T dash over T is half. So when you put half there, half 12 over 14. 6. We have 3 by 7. 3 by 7. I have to take the square root of that. 3 by 7 means 0.4, then 20, 2, 60, 8, 40, say 6. I will get the square root of this. So 0.6, 0.7, it's in between 0.6 and 0.7 because 0.6 square root will be 0.36. 0.7 square root is 0.49. Let's check 0.65. 5, 5, 25. 6. You multiply by the next number. 7. 6, 7, 42. 4 decimals. 0.4225. It's quite close, right? 0.4286, 0.4225, it's quite close. Up to 2 decimals, it's the same. Then I can say it's 18 into 0.65. 18 into 0.65. Multiply 18 into 5 is 90. 18 into 6 is 108 plus 9, 117. correct? No, 11.7 meter per second. Check again. 18.5, 90, 9 balance, 108 and 9, 117. 2 decimals you have to bring forward. 11.7 meter per second is the speed when the tension is changed. Students, you can see I have made the arrangement now. Let's first understand the arrangement here. On this side, this is what we call the vibrator. It's basically a motor. When it's given the electric power, it vibrates up and down like this. So that vibration is going to generate a wave along this string. The wave will be traveling all the way up to here, right? This is the string we have. On the string, the wave will be traveling. And on the other side of the string, we have a pulley. Along the pulley or above the pulley, the string goes, and on the other side, we have a mass holder and few masses are attached to that. Few weights actually. Why do we attach these masses? To give a tension on the string. You remember the velocity of transverse wave along a string we studied, V equals square root of T over M. T is the tension on the string, M is the mass of the string per centimeter or meter, per meter. That means for unit length, the mass. V equals square root of T over M. As long as I don't change this string, M doesn't change. Mass per unit length doesn't change. But I can change T by adding or reducing the weights, masses I attach on this mass holder. The tension is going to be changed because you know at this point if you take the equilibrium, T is upwards, mg is downwards. So T should be equal to mg. You increase the tension by adding more and more masses to it. You reduce the tension by reducing the number of masses you add here. So V equals square root of T over M. By changing T, you can change the velocity of the wave along this string. On the other hand, this vibrator, we can change the frequency. There is a particular limit within that I can change the frequency. How many times per second the vibration takes place, I can adjust it. So see, like we have V equals F lambda equation. Let's say first I keep frequency at a constant value and I change V. I keep changing V by adding or deducting the mass here. So when V reduces, F is constant, which means lambda has to reduce. Wavelength of the particular wave becomes shorter and shorter. Then within this length of string, I will be able to see more nodes. Right? When I keep the tension very high, velocity is high, I will be able to see only one node here. That's what we call fundamental node. Fundamental node. Then little by little when I reduce the mass suspended here, tension reduces, lambda reduces, I will be able to see more and more nodes here. First overtone, second overtone, third overtone, I will be able to see. At this point, you must understand one concept called standing waves. The wave that travels in this direction, after it reaches this end, it will reflect. So what is standing wave? When a wave or when two waves with same frequency and same amplitude travel through the same medium in opposite directions. They generate a standing wave. We will be able to see standing waves here. With the standing wave only we can understand the first overtone, second overtone, fundamental note, all that. This is keeping the frequency constant. By reducing the tension, you can increase the notes. Similarly, keeping the tension unchanged, you can adjust the frequency also. Why? When tension is unchanged, velocity is going to be constant. When velocity is constant, v equals f lambda. When f increases, lambda should reduce. When lambda reduces, you should be able to see more and more wavelengths within this length of the string. Right. So, that is what we are going to see. We are going to observe. No readings to be taken, no calculations to be taken. We can do calculations like you can find the lambda, you can find t, and you can do few calculations as well. But the main purpose is not to do the calculations here, to understand the basics that we studied as the features of waves, basic features, basic properties of waves that we are going to understand here. Right. So, first I am going to switch on the vibrator, and one more thing you need to understand here, the weight actually you have to adjust by smaller quantities. The mass has to be adjusted little by little, because when you exactly get the same tension, then only you will be able to see the fundamental note, first overtone, second overtone and all. Let us say for example, for the first overtone, let us say you need 120 Newton on this string. Suppose you are changing 50 by 50. You add 100 Newton, then you go to 150 Newton, you won't be able to see that overtone. Understand? At least, if it is 120, you must be at 115, 120, 125. Around that figure, you have to have the tension on the string to see that overtone. That's why I say when you are changing the mass, we have to change by smaller quantities, smaller masses. So, I am going to change it by 50 gram by 50 gram. 50 gram means 50 by 1000 into G is 10. So, basically 0.5 Newton by 0.5 Newton, I am changing the tension, which means I should be able to see almost all the overtones, right. So, first I am going to see keeping frequency constant by changing the tension. Let us see whether we can observe the fundamental note, first overtone, second overtone. Let us see if we can observe it. Students, now you can see I have adjusted the frequency for the given weight and I have got the fundamental note here. Fundamental note. You can see there is only one half of a wave you can see. Since it's a standing wave, you can see the upper part as well as the bottom part of it. Can you see somewhere here the amplitude? You can see the displacement is maximum. That's what you call amplitude. And here close to the ends of the string, the point is almost stable. The amplitude is almost 0 at that point. The displacement is almost 0. That's what we call the nodal points, the nodes. Right here we say antinodes, and that is the nodes. Antinode is where the amplitude, you can see the displacement being maximum. Right. Now, as I mentioned earlier, let's reduce the tension here. Let's reduce the number of or reduce the mass that has been attached here, so that T reduces. So, lambda will reduce, then the wavelength has to reduce. Then I should be able to see more nodes here, right. Shall we see how it works? Let me reduce the masses attached here. Students, now you can see we have the one full length of wave here, right. In the middle here you can see a node. It's a nodular point where there is no displacement. All the points here do not displace. And there are two antinodes here. Can you see? That is where the amplitude is. The particles there have the maximum displacement. So, what did I do now? I reduced the tension and increased the number of nodes we get here. Right. Next, we will see how we can get 3 nodes here. Students, now you can see there are 3 half wavelengths here. This is one half wavelength, another half and one more half. What did we do this time? We reduced the mass attached on this mass holder so that the tension reduces. Because if the tension reduces, lambda reduces. So, this is what I told you earlier. We can keep the frequency constant, and by adjusting the tension in the string, we can increase or decrease the lambda and get more nodular points. Look at these 2 points. These are the nodes. Nodular points we say, where the displacement of the particles is 0. They don't get displaced at all. This is an amplitude antinode point. Amplitude we say, maximum displacement you can observe. There are another 2 more points like this. Right? Now, I have switched off the vibrator.
Now what did we do? We kept the frequency constant and we adjusted the tension and we were changing the lambda, changing the wavelength. Similarly, you can keep the tension constant, right? You don't have to change the number of masses attached on this side. You can adjust the frequency at the same tension. By adjusting the frequency, you can change the wavelength as well. Why? In V equals F lambda, V is square root of T over M. T is the tension, so if you don't change the tension, V doesn't change. Keeping V constant in F lambda, you increase F, lambda has to decrease. Right? Then you can see the fundamental note, increase the frequency more, then you can see the first note, first overtone, second overtone, all that. In the similar method we have seen now, we can see by changing the frequency also. Right? So this is what we say, properties of a transverse wave that travel through a string. And you clearly observed how the standing wave was created. What was the basic principle of standing wave? A wave or two waves with the same amplitude and same frequency traveling in opposite directions through the same medium will create a standing wave. So what we observed just now is exactly the phenomenon of standing wave. Right? So that's all about the transverse waves I can show in this vibrator. Next we will see how we are going to observe the longitudinal waves. Students, you can see this is what we call a slinky. You can find this in all the science laboratories. Even though you find it in the laboratories, it was originally invented as a toy. In 1940, by a toy manufacturer, it was invented. But why we use this in the laboratory now? It's useful to understand several properties of waves, right? This can be used to understand properties of transverse waves as well as longitudinal waves, especially longitudinal waves, because when you say transverse wave, the particles vibrate perpendicular to the direction of the wave. That's why we draw it as a sine wave, where if wave travels along the x-axis, the particles on that medium, they vibrate perpendicular to that. So in the y direction, you can see the vibration. This is what we call transverse wave. Even when we did with the string, you could see that the string goes in one direction, whereas the particles vibrate in a perpendicular direction. That's the basic feature of a transverse wave, which we can observe on a slinky as well. Then how about longitudinal waves? In longitudinal waves, the particles vibrate in the same direction where wave also travels. So if the wave travels in the x-axis, particles also vibrate in the x-axis itself. They don't vibrate in the opposite direction. So it's actually one-dimensional. One-dimensional. The waves travel, or the vibration travel in one direction, and the particle also travels in the same line itself, not on another plane, right? Which we can very clearly observe in a slinky, right? So now we are going to see how a transverse wave travels, and we can see the fundamental note, first overtone, second overtone, all that in a slinky, plus how the longitudinal wave travels on a slinky also we can observe here. Let's see how it is going to work. And you know, this slinky, if you extend it, it can go for meters and meters. Even for 100 meters, you will be able to extend it. But you have to be very careful when you are using it in the laboratory, because if you take a very small section and extend it too much, it will get distorted. So if you distort one part of this slinky, then the property of this slinky will be affected. So you will not be able to observe all the waves properties using this slinky. So you have to make sure when you are using this slinky in the laboratory, you have to remember the following batches also have to use the same slinky. So learn how to use it without damaging the properties of the slinky. That's very important. Not only slinky, whatever the apparatus you use in the science laboratory, you have to ensure after you use it for the experiment, you restore it in the same way it was there, so that the following batches also will be able to use that. Right. So now when we use this laboratory, usually what we do in the laboratory, from one wall to the other wall, we extend it and we do this experiment. Usually 2 people will be holding it, 2 students will be holding it, and that's exactly the same method. I'm going to do it here as well. You can observe most of the properties of waves now. Students, now I will show you how a fundamental note can be observed. Transverse waves, standing waves, fundamental note, how we observe, you can see it now. You could see only a half of a wavelength, and there was antinodes in the middle and the nodes on both ends. Only lambda by 2 length you were able to observe of this standing wave. This is what we call fundamental note. When we say first overtone, you can see one full wavelength. In the middle, you can see one node. On both sides, you can see another 2 nodes. So altogether 3 nodes will be there, and 2 antinodes you will be able to observe. We call it first overtone. Let's see how we can observe first overtone on this. So what happens here, the other end, the student who is holding on the other end, he is just keeping it stable. I give the vibration from here. So vibration travels to the other end, it gets reflected from there and it returns. So with the same frequency, with almost same amplitude when it returns, that is where we see the standing waves. Right? That's why you are able to see the upper part. When you do it faster, within the same lambda by 2 itself, you can see the upper part and the bottom part of it because of the standing wave phenomenon. Right? So now you saw first overtone. This way we will be able to observe second overtone, third overtone, all that using a slinky. Now this is transverse wave. You saw when the wave travels in this direction, particles vibrate perpendicular to that. Now let's see how a longitudinal wave travels. Right? So you can see when the vibration that I start here, it keeps moving all the way up to the other end. Since the other end is stable and rigid, it gets reflected from the other end, it comes back. Right? You can observe the wave goes all the way. So the particles do not vibrate perpendicular to the slinky, they vibrate along the slinky itself. Right? That's why you can see at some places there will be a congestion. The slinky that get congested at a place. Then when the vibration moves to the other point, next point, it gets congested there. Likewise, it keeps moving. So a small congestion that moves all the way and it gets reflected on the other side and it returns. You can see that once more. That's how it works, right? That's a longitudinal wave. So at this point, when I say that for a transverse wave, particles vibrate perpendicular, and longitudinal wave, it vibrates along the slinky itself. If we keep 2 blocks on either sides of it, right, on both sides of it, if we keep 2 blocks almost touching this slinky, and then when I vibrate it, if it is a transverse wave, it will not be able to go passing that block. Why? If I keep 2 parallel blocks here, that will prevent perpendicular vibration. So the transverse wave will not be able to pass that point. Whereas longitudinal wave will be able to pass because it doesn't vibrate perpendicularly, it vibrates along the slinky itself. So keeping 2 parallel blocks will not prevent the traveling of longitudinal wave. Let's observe that now. You can see, as I mentioned, I have kept 2 bases of stands as the blocks here. Now let's send a transverse wave and see what happens whether it goes passing this block. You could see that I gave the vibration from this end. it was vibrating up to this point, but it couldn't go passing this point because the vertical vibration or the vibration which is perpendicular to this slinky cannot go passing this point. Whereas now I will send a longitudinal wave, you can see the vibration I gave here will be passed all the way even after this block as well. Right. So, you could see that the vibration I gave it here, it went passing this all the way to the other end and it got reflected as well. Right. So, this is what we said. In a transverse wave, the particles vibrate perpendicular to the direction that waves travel, whereas if it is a longitudinal wave, the particles travel in the same direction where the waves travel. Clear? Right. So, that is all the properties that we can easily observe about the waves using slinky as well as a string, right. So, this part usually does not come much in the structured essay type of questions, but then in MCQs these are tested frequently, and even in some essay questions some parts are tested on this. So, obviously the learning that you have got from here will be useful in some parts of your exam, right. So, go through this couple of times, practice this very well, and let us meet up with another experiment in physics.
That's all in that question. Now look at this one. That was 1988. This is 1997. A sonometer wire is stretched between points A and B that are in 1 meter distance. When the string is plucked at its midpoint, it vibrates at first harmony as shown in the diagram. The string is vibrating in simple harmonic motion in vertical plane. This motion is given by A equals 16 pi square into 10 to the power 4 y. Here A is the acceleration and y is the vertical displacement. Okay, A is the acceleration, y is the vertical displacement. Alright. Draw a rough sketch to show the variation of y with time t. Y is the vertical displacement. If you take a particle here, initially it's at 0, like same point, then it goes up, comes down, goes up, that's how it's going to. So, if I take upside as positive, it goes up, comes down to 0, goes down in negative and comes up. A sine wave, that's how it's going to continue, right? Calculate the period of oscillation for the vibration of the string. Period of oscillation. So, T equals 2 pi by omega. I need to find omega now. Omega. Omega for a simple harmonic motion, we write omega as, look at this, A equals, acceleration equals, A equals omega squared into displacement, correct? That's what the formula should be. A equals omega squared into y. So, omega squared must be this much. Omega squared must be 16 pi squared into 10 to the power 4. So, that's 4 pi into 100. Substitute here, 2 pi over 4 pi into 100. 1 over 200 seconds. 1 over 200. There's period of oscillation. That means for one full oscillation, for the particle to go up, go to the least point, lowest point and come back to the midpoint, right? That's 1 by 200 seconds it takes. Find the frequency. Frequency is F equals 1 over T. 200 hertz. 200 hertz. Within 1 second, 200 times it's going to oscillate. 200 hertz. What is the wavelength of the wave produced? Wavelength of the wave produced, V equals F lambda. Oh, we don't need V equals F lambda, because what we see there is the standing wave. Go and see that. This is the standing wave. And what we see here is lambda by 2. Half of a lambda is what we see, and that's 1 meter. That's 1 meter. So, we can say lambda by 2 is 1 meter, lambda is 2 meters. Lambda is 2 meters. Find the velocity of the transverse wave in this string. V equals f lambda. We know the f, we know the lambda. Substitute. F is 200, lambda is 2. So you get 400 meter per second. 400 meter per second. Write an expression that relates the speed of transverse wave tension T in the string and unit length mass m of the string. The one we always study, V equals square root of T over m. Careful, this is unit length mass m. So I don't have to divide by the length. If they have given the total length, then you have to divide by the length. Total mass, then m over L has to be applied. If m is 1 into 10 to the power minus 4 kilogram per meter, what's the tension in the string? V equals square root of T over m. We got V to be 400, T over m, 1 into 10 to the power minus 4. 10 to the power minus 4. So it's going to be 400 squared T into T divided by 10 to the power minus 4. When you multiply here, both zeros, 0, 0, 0, 0 will be cancelled. T is going to be 16 Newton. Tension in newtons. 16 newtons. Can you understand? These two zeros will get cancelled with that 10 to the power minus 4. So only 4 and 4 would remain, which is 16. When the students were asked to resonate the sonometer using vibrating tuning forks, they followed the following steps. Holding the tuning fork just above the midpoint of the string. Keeping the tuning fork on the midpoint of the string. Keeping the tuning fork on the sonometer box. Which one of the following in the above methods are right? Which of the following methods are right? Explain your answer. How do we keep the tuning fork? We keep it always on the box, not raised up, because then only from the tuning fork the energy will be transferred into the sonometer box with highest efficiency without much loss. If you hold it up, what happens? From the tuning fork, energy will be transferred to the air. From the air only it will be transferred to the box. So when it transferred into the air, it gets diffused. It gets diffused to all the air particles. Then the energy that goes into the sonometer box will be much less. To avoid that, we give direct contact between the tuning fork and the sonometer. So let's say third one, method 3. Why? To maximize the energy transfer from tuning fork to sonometer. Next one. What is the lowest frequency of the tuning fork that will resonate with this sonometer? Now look at this. The resonance that you can see, this is going to be 1 meter. One case is this, first harmony. Then you can see first overtone. Then you can see like this. Right. So here lambda is going to be 2 meter. Here lambda is going to be 1 meter. The entire lambda. Here 1 meter is 3 lambda by 2. So lambda is going to be 2 by 3 meter. Right? But V is constant, right? V is what? Square root of T over M. T doesn't change, M doesn't change, V is constant. Then when lambda reduces, frequency will increase. Frequency will increase. Right? So when lambda increases, this is the highest lambda. That means that will have the lowest frequency. That will have the lowest frequency. Highest lambda will have the lowest frequency. Highest lambda will have the lowest frequency. So what is the lowest frequency of the tuning fork that will resonate? So you have to understand this case. That means the fundamental harmony is where we are going to have the lowest frequency that resonates. V equals f lambda. We found it, I think, isn't it? It was 200 hertz. We don't have to redo it. 200 hertz. 200 hertz. That's the answer. You don't have to write all this. This is for you to understand. Just 200 hertz would be enough. When you go to the next one, if you won't just do it, V equals f lambda. V is 400. Now let's say f1. Now lambda is 1, right? So f1 is going to be 400 hertz. So here 200 hertz will resonate. Here 400 hertz will resonate. And here it will be again higher. It's going to be 600 hertz. It will be here. If a paper rider is kept on the string at its midpoint, at what minimum displacement would the rider start to fly away? This is a question connected to mechanics. They have given you a hint also. The rider will fly away when the reaction from the string on the rider is 0. Hold on. Let's try to understand this. This is how the string is going to be. This is how the paper rider is going to be on top of it. What are the forces acting on this paper rider? It will have weight. It will have normal reaction from the string. This is the string. Right. So, imagine the situation when it goes down with A. Let's apply F equals ma downwards. W minus R is going to be ma. But what we say here, the moment that this rider leaves this string, the reaction has to be 0. The reverse of that, when the reaction becomes 0 only, the rider will leave. So when they say the rider flies away, I can say R is 0. This is 0. Then you can say W equals ma. Why is it 0? Since the rider has to fly away, the reaction has to be 0. That's what the note also says. The hint also says that. Right. W, let me say mg. They asked. What's the minimum displacement they asked? Okay, mg. M into A was given, remember, 16 pi squared into 10 to the power 4 y. Remember? That was the equation for acceleration they gave. M and M will be cancelled. Pi squared and g can be cancelled because pi squared is almost 10. 3.14 squared is almost 10. So you need to find y. Y will be, if you bring everything to the other side, 1 over 16 into 10 to the power 4. 1 over 16 means, it's 0.0625. 0.0625 into 10 to the power minus 4. 10 to the power 4 goes up minus 4 meters. Right. So, this will be, if I multiply by 1000, I can write in millimeters. So, if I bring it here, 62.5 into 10 to the power minus 4, 6.25 into 10 to the power minus 3 millimeter. 6.25 into 10 to the power minus 3 millimeter would be enough for the particle to leave. Okay. So that's the mechanics question. That's not much connected to the waves and oscillations. They are asking when the particle would leave. So you have to apply F equals ma, where when you analyze F, the reaction has to be 0, which you don't really have to remember from mechanics. They have given you a clue there. When the paper rider flies away, the reaction is going to be 0. So when the reaction is 0, the weight and ma has to be equal. Weight means mg, m and m cancels. Pi squared and g are almost same values. You can cancel them and then you get the answer. That's all about that paper. Let's move on to another one. So quite easy ones, straightforward easy ones. Look at this. Year 2000. A student is planning to do an experiment to find the frequency of a tuning fork using the sonometer. Where should he keep the tuning fork to get the resonance? On the sonometer box. We have discussed this several times. We have analyzed this in the other experiments also. Please go and see like where we have used the sonometer and tuning fork, the experiments we have done. right? You will understand where we keep it. Even though in this experiment we have not discussed that, in the other experiments we are using the tuning fork to resonate with the sonometer. We have done it. We have done 2 experiments like that. What procedure should he follow to get fundamental resonance length? So how do we get the fundamental resonance? Fundamental resonance means this scenario. So how do we do it? You keep the bridges very close, right? You keep the bridges very close. Keep a paper rider on top of that. Then vibrate the tuning fork and keep it here, right, on the box. And then slowly increase this gap between the bridges until the paper rider is thrown away, until it flies away. The moment it gets thrown away gives you the first occurrence of resonance. First occurrence of resonance means that has to be fundamental resonance. So let's write it. Keep the bridges at minimal distance. At minimal distance and place a paper rider on the string in the middle of bridges. In the middle of bridges. Vibrate the tuning fork and place it or keep it on the sonometer box. And increase, so here let's not say and here, vibrate the tuning fork, place it on the sonometer box and increase the gap between the bridges until the paper rider is thrown away. This instance is fundamental resonance. Fundamental resonance. Clear? Right. So this we did not discuss in this experiment. We have done this in another experiment. You can always go back and check those other experiments where we have done this procedure. Right. The student used different weights and found the fundamental resonance lengths for different tensions in the sonometer wire. Write an expression relating MLF and unit length mass M of sonometer wire. They say write, so you don't have to derive it. You can straight away write it, but let's see how to derive it. V equals F lambda. V is going to be square root of T over M. T is mg. That's the weight they are connecting. And then unit length mass is M. F into lambda will be 2L, right? Because fundamental resonance, L is going to be lambda by 2. Lambda is 2L. So F is going to be 1 over 2L square root of mg over M. Square root of mg over M. Out of the L values he obtained, which can be assumed to have highest accuracy? The highest L value he has will have highest accuracy because the fractional error will be less. Fractional error. Why? Fractional error is error, reading error divided by the measurement. See, you are going to use a meter ruler to get the measurement. Meter rulers have 1 millimeter as its least count. So, the error is always constant. Error is constant. 1 millimeter is the error. Maximum possible error is 1 millimeter. And then the measurement we take, if you can increase that more and more, then what will happen? The percentage error or fractional error can be reduced. So, they are asking which length out of the L values you obtain, which can be assumed to have highest accuracy, the highest L value. Highest L value. Give reasons for it. It will have the lowest fractional error. Lowest fractional error. The diagram shows the graph that student drew in this experiment. P centimeter squared M. Let's see how P and it can't be P, it has to be L squared. Yes, L squared. L squared and M. The graph, the equation we had was this one. F equals 1 over 2 L. F equals 1 over 2 L square root of mg over m is the equation we had. Let's rearrange it now. L squared, right, 1 over 4 f squared. I squared it, so 2 will become 4, f will become f squared, g over m into m. Y equals mx. L squared in the y-axis, capital M in the x-axis, y equals mx. The gradient is going to be this. G over 4f squared m. Right. Let's see. Mark 2 points on the graph that you can use to find the gradient of the graph. So, usually I always tell this, when you mark 2 points on the graph, how you have to mark it. Look at this. If this is how the grid is, right? If the graph goes like this, rather than taking this point or this point is ideal because it goes through the intersection of a vertical line and horizontal line, right? So, it's easy for us to read the x and y coordinates of that point. So, that's what they expect you to choose it carefully. So, here in the graph I have, right, the one I have in the diagram here, this point seems to be a good one. That goes through 7 and 850, is it? 850. Let's take another point somewhere down here. Maybe this point is good, 1 and 100. So, the gradient is going to be, mark 2 points. They simply ask you to mark, okay? And then they will ask you to find the gradient. Find the gradient, yes. So, the points we have 1 and 100. Other one is 7 and 850, isn't it? Let's check. 7 and 850. 7 and 850, yes. So, the gradient is going to be 850 minus 100, 7 minus 1. 750 over 6. 125. 125. If the value of m is 8 into 10 to the power of minus 4 kilogram per meter, find the frequency of the tuning fork. So, you know gradient equals square root of, did we have a square root? No. The gradient was g over 4 f squared m. G over 4 f squared m. Careful, the units of this gradient, this is in centimeter squares and this is in kilogram. See, centimeter squares and kilogram. Let's mark that. Centimeter squared per kilogram. So, if I change this to meter squared, because later, like when we apply it here, These are all going to be in kilograms, meters, yes, and seconds. So, meter squared means 1 centimeter is 10 to the power minus 2 meter. So, centimeter squared has to be 10 to the power minus 4. 125 into 10 to the power minus 4 meter squared over kilogram. So, let us write it here. 125 into 10 to the power minus 4, G is 10, 4F squared, M is 8 into 10 to the power minus 4. Take F squared here. Look at this. 10 to the power minus 4 will come up here as 10 to the power 4. This will also go 10 to the power 4, 10 to the power 8. This 10, I will keep it separately. Let's see what we can do with that. 125 into 4 is going to be 500. 500 into 8 is going to be 4000. 4000 divided by 10 will be 400. Check that. 4 into 125 is 500. 500 into 8 is 4000. Top you have a 10. So, 4000, 1 0 will be cancelled, 400. F is going to be 10 to the power 4 divided by 400 square root will be 20. So, if I take it as 100 into 100, it's 500 hertz. 10,000 divided by 20 is 500 hertz. So, use some techniques when you are solving it. Remember, F squared is there, I have to take square root. So, wherever you see squares, keep it. That's why I kept 10 to the power 8. I didn't want to keep 10 to the power 9. If you keep 10 to the power 9, when you take square root, it's difficult. If you have even powers, 10 to the power 8, 10 to the power 6, then divide the power by 2 and that's the square root. 10 to the power 8, square root is 10 to the power 4. Right. Next. This is 2003 paper. You are asked to use a piston with a glass tube and a set of tuning forks available at your laboratory to learn about the concept of resonance in sound. The piston is free to move within the glass tube. Refer to the diagram. Okay. So, this is the glass tube. This is the piston. Piston can move in and out. This is length L. Right. So, you remember, like in the other experiment, we used the resonance tube where we kept a PVC tube within a water jar and we were raising the PVC tube or we were raising it up and down to change the length of the air column that resonates. See, they are doing the same thing, not with water jar here. They have a piston. So, by moving this piston in and out, you can change the length of air column that's going to resonate. Clear? And this is the set of tuning forks they have given to you. Let's see what questions they ask. All the resonance tubes are made of the same material and the forks have same cross-sectional area. If the frequencies of the tuning forks are known to be 256 Hz, 384 Hz, 512 Hz, 420 Hz and 320 Hz. What is the frequency of the tuning fork B? You know, A should have the highest frequency because when the length of the fork becomes shorter and shorter, frequency increases. So, A will have the highest frequency, B will have the second highest frequency. Go and see where second highest is. 512 is the highest. 420 is the second highest. So, B will have 420 Hz. 420 Hz. Briefly explain how you would obtain the resonance length for fundamental resonance L for given tuning fork. The other experiment we have explained this. What do we do? Keep the resonance tube. Initially, the length of the air column must be much lower, minimal level, and then vibrate the tuning fork and hold it on top of it, right? Hold it just above that air column, and then increase this length. That means pull the piston down. Slowly you pull it until the point where you hear the highest sound, right? The intensity of sound will be high at one point. Suddenly you will hear a increased intensity of sound. Until that point you are going to increase the length, right? So, let us write it. push the piston and keep L as low as possible. Vibrate the tuning fork and hold it above the tube. Pull the piston slowly to increase L until an increased intensity of sound is heard. This instance will be the fundamental resonance. Fundamental resonance. Next, in finding L note in B1 above, instead of ear, a sound measuring apparatus is kept near the open end of the tube to record the sound intensity S when L is changed. Draw a rough sketch of how S changes with L at L note and around L note. L note is what? L note is where the fundamental resonance takes place. So at L note, you will have very high density of sound or intensity of sound. So what happens? See, if this is where L note is, see, like the points before that you will not have any sound, or you will have a very low level of sound. Right close to L note, you will have a high intensity of sound like this. Understand? So that's what they asked you to mark here. See, at L note you have a high intensity. Just before that and after that, it falls down to a different level. What is the length of first resonance in terms of L note? What is the wavelength of first resonance? Okay. So, you know, you are going to have like this. This is L note. Right? And this is what? Lambda by 4, isn't it? So, lambda by 4 is L note. Lambda is 4 L note. 4 L note. Show the variation of S with L for the first overtone in the same graph. Compared to fundamental overtone, this we have done in the other experiment. Compared to the fundamental overtone, when you come to the first overtone, the intensity of sound will be less. It's very easy to observe the fundamental resonance, but the first overtone, it's pretty hard because the intensity will be less. The reason is, fundamental resonance, only a small air column resonates. So, the energy transferred from this is going to be distributed among a small column of air. But when you go to the first overtone, you will have like this. A longer column of air has to resonate. That means there will be more air particles in it. So, the energy transferred is going to be distributed to more particles. So, the energy each particle gets will be less. Right. So, the amplitude they are going to vibrate will be less, which makes less sound. Right. So, how we mark this on the diagram? See, first overtone, or we need to find the length as well. Look at this. Length is going to be, if this is L note, right? Understand we have three parts like this. So, it's going to be 3 L note here. So, first overtone happens at 3 L note. 3 L note. Right? The intensity of sound has to be less, not at this level. I'll mark it here. Right? Similar pattern is there, but not at the same intensity. At a lower intensity, it should be there. Right? So, two things you have to understand. At L note, if you have the fundamental resonance, first overtone happens at 3L note. At L note, if this is the intensity of sound you hear, in the first overtone, the intensity is much less. Next. Assume that you have to find the velocity of sound in air using all of the above given tuning forks. Which of the above tuning fork is most appropriate to be used first when finding the velocity of sound using a graphical method? Remember, we discussed this in the other experiment. This is lambda by 4, which is L. Lambda is 4L naught. V equals F lambda. V is constant. Right, V is constant. So when F increases, lambda decreases. So if you take the highest frequency, you will have the first resonance at shortest L note. Right? Let's say 520 Hertz you take first. Let's say you have L note. Then you take 480 Hertz. Let's say it's L1. The first resonance, fundamental resonance length is L1. Definitely, I can say L1 is greater than L note. Definitely it will be greater. So what's the implication for us? What's the advantage? You do it for 520 Hertz, you get L note, and then to do it for 480 Hertz, you don't have to go back to the original position again. See, you kept the piston like this and you are pulling it. When you do it for 520 Hertz, let's say your piston has come to this point. This is where the piston is. And when you move on to 480 Hertz, you don't have to go back to this position again. From this itself, you can pull it downwards because you know the L has to be bigger for 480 Hertz. After that, if you take 420 Hertz, I'm just putting some numbers, the length will be even bigger. Right, that's why we keep the frequencies in the descending order and take the highest frequency first so that it will have shortest length, and then in the order we will be getting the first resonance to everybody. So they ask which are the above given tuning fork, the highest frequency. What's the highest frequency? I remember 520 Hertz was there. 512. 512 Hertz. To make your results more meaningful, there is another physical quantity that you have to record and publish in this experiment. What is that physical quantity? You are finding the velocity of sound, right? Velocity of sound is related to the temperature as well, right? So when you are doing this experiment, on a separate note you have to say, when I did this experiment, I got velocity like this, okay. I did this experiment at this temperature. Because one student does it at 30 degrees, another student does it at 34 degrees, another student in another area, another region does it at 25 degrees. Velocity of sound will be different. It will not be same. So the outcomes you get from the experiment can be different for each of you. Therefore, when you are publishing the velocity of sound in air, we always have to mention, okay, we did the experiment, we got the velocity by like this, and the temperature was this when I did the experiment. Right. So what's the other quantity that you have to publish? Temperature. The value of S is observed to be 60 decibels in one of its instances of B2. If the threshold of hearing is 10 to the power minus 12, find the intensity of sound in the above instant. So you know decibel is written as 10 log intensity over threshold intensity. So here 60, 10 log intensity is what they ask. Threshold intensity is 10 to the power minus 12. Solve it. This is base 10, right? So it's going to be 10 to the power 6. Cross multiply. 10 to the power 6 into 10 to the power minus 12. 10 to the power minus 6 watt meter minus 2. Clear? Right. So, those are some past paper questions somewhat connected to the experiment we have done, where we learned about the properties of waves. Right. So, practice all these waves and oscillations. The structure questions are quite easy, straightforward ones. You should be able to get full marks without a problem. Practice all these. Next, we will meet up with another experiment.